Hello, folks. This is the continuation of a video series segments that I'm making for uh, uh, performing vibration, simple single degree of freedom vibration in the Catia program. Now, I call this series the Killing of a Fly with a Cannon series because it's the kind of thing that you really don't want to do with a sophisticated FEA package, but these analytical solutions exist, and you can actually look at any vibrations book, first few chapters, they'll give you this information. However, my philosophy is that if if we are to trust this calculation that we're doing for more complicated problem, we might as well be able to confirm that it actually works for a single degree of freedom system. Now, because um, the usage of the for example the embedded FEA program in Catia is not intended for a simple problem. There are some hoops that you have to go through, but uh, essentially it is not a big deal. The previous videos that I've done, I mostly assumed that the damping was zero. Okay, there was no damping. So this time I'm going to assume that there is a damping, and also there are initial conditions specified. Okay, so there's initial displacement, initial velocity specified, as if you move the mass, for example, from this equilibrium position, and then give it a velocity, initial velocity, and just let it vibrate. And this, obviously, because of damping, the vibration amplitude is going to reduce. Okay, so here's the problem. These are the numbers that I'm going to be using. So the mass is 1.553 slugs, and there's the stiffness of the spring, and there's a 1% damping ratio. And this can be solved analytically. I mean, you can find it in any vibrations book. Oh, by the way, I forgot to say that the initial conditions are given here. So you displace the mass by, for example, a tenth of a foot, and then you give it a velocity and just let it vibrate. So here's the analytical solution, and these are the information that we need in order to basically solve a problem like this analytically. You need the natural frequency of vibration. This is radians per second. Here is hertz. These are the undamped natural frequencies. And there's the period, natural period is about 0.78 seconds. Damping ratio, this is damp frequency, which you can see that it appears actually here. That's supposed to be this number, although this is written to 4 digits. That's why this is rounded. And then there's damping frequency in hertz, and then damping period in seconds. Now, the problem with the Catia is that it assumes that the initial conditions are zero. There is no provision for specifying initial conditions in Catia, initial displacement, initial velocity. So, and it uses the linear dynamics concepts, and therefore the Duhamel principle or Duhamel integral. And that being the case, we have to somehow trick the program to take into account these initial conditions, and this is how we're going to do that. This F is force applied during the vibration. Now, in this particular problem, this external force. This is a free vibration. Therefore, there is no external force. So that's why we have to fool Catia so that there is a force that moves this thing to the right, for example, about 0.1 feet per second, and give it an impulse, basically a force over a short duration of time, so that we have an F here. Okay. Now, here is the F that I'm going to be using. So the first Tn seconds, okay, Tn seconds, we linearly, or let me put it this way, we apply a force which linearly increases the displacement until the displacement reaches the 0.1 feet that we want. And at that point, it gives it an impulse, which means a big force over a short duration of time, and that results in the velocity of 6 feet per second. And then as soon as that's done, then the force drops to zero and stays zero. So basically, it is a free vibration problem. Through this tool, we are tricking it to do the initial displacement and initial velocity, and then the force drops to zero. Basically, we have a free vibration problem, damped free vibration problem. Now, in order to do these transient dynamics problems in Catia, which means give me a force and find out what the displacement is, you need to have a modulation. The modulation is the variation of force versus time. So based on what I showed you here, I have to create an Excel spreadsheet with these columns. This first column is the time, and this second column is the essentially the magnitude of the force. Okay, and now a couple of things. The zoomed in view, except that it's not to scale, is this linear variation. Now remember, I want to push this thing to 0.1 feet. Now this is force, so I have to multiply it by stiffness, which was 100 times 0.1 is going to get 10 feet. So linearly increasing to 10 pounds. And then this impulse, which is equivalent to that force, over that short duration of time, and then drops to zero. So that's the same thing as before, except that it's zoomed in and not to scale. Now, you have to be careful about the number of steps that you use. So I don't know exactly what you're going to use. Usually you start with something and then you increase it until things don't change that much. So that tells you basically you have reached the acceptable level of number of steps. And I have a choice of doing rigid spring or spring rigid or rigid spring rigid or spring rigid rigid spring. But I'm going to be using spring rigid essentially element to model the behavior of uh, the spring. Okay, and we're going to come to these later on. Now, before I do that, actually, let me remind you that this problem, if it's done with zero damping, okay, notice that zero damping. So we over one period we increase the displacement to 0.1 feet, and then because and give it an impulse, no damping, so it follows the actual solution very closely. But when there is damping involved, for example, 1% damping that I have, so notice that 1% damping, the magnitude of the oscillation reduces, but there is a difference between slight difference between the analytical solution and the Catia generated solution, which is this red one. Okay, as the level of damping gets higher, this gets worse. Okay, but there is a catch here. There is a catch here, and we're going to talk about that later on. So these are for different levels of damping. You can see that the red one is Catia generated, although mind you that this is not calculated from Catia. This is done on a MathCAD program because Catia does the same thing. It's just that I didn't want to generate all these things in Catia. I'll do one of them, and then I'm pointing out to the issues here. So you can see that as the level of damping gets bigger, this discrepancy between the analytical solution and exact solution becomes more. However, there is a catch here, because in the first period, when you increase the force from 0 to that 10 pounds, damping is also applied to that portion of the graph, because the Hamel integral starts integrating from 0. Okay, although I'm doing one period here, 0 to about 0.7 seconds, which is linearly increasing, damping comes into the picture. So if I shift the analytical solution, if I shift this green solution is the analytical solution. If I shift it by one damp period, notice that they match perfectly. The dotted one is the shifted analytical solution by one period, damp period, and or undamped period, doesn't matter. And then the red one is analytical solution, the Catia generated solution, although this is not Catia. Okay, but the same thing is going to happen in Catia. I'm not going to create all these graphs in Catia. I'll just do just one of them with the 1% damping, and I'll leave it to you to investigate. If you investigate it, it will come up with these graphs. Okay. Notice that even high level of damping, this thing still works. And yep. So let's go ahead and do this. We're gonna. I have already changed my units, by the way, so that things are in feet and slides and things like that. So you click on it, click on the point. This is the first point. This is the wall, basically. You do another point. I'll make it point, I don't know, 0.2 feet. And there is the the place where the mass is located. Draw a line, going from here to there. These are pretty much the same steps that I'm doing in the previous videos on single degree of freedom and tricking Catia to do it, except that we're undamped. All right, now we're going to apply a material, dummy material on it. So I'll use aluminum on that. However, I'll change the properties of the aluminum so that essentially they have no stiffness, very little stiffness, and a very little mass, so that they don't mess up the single degree of freedom calculation. So this one, I'm going to make it 0.1. This is Young's modulus. And this one, I'm going to make it 0.1 kilograms. So essentially, I've reduced the stiffness of the aluminum by about 7 orders of magnitude, and this one by 3 orders of magnitude. Unfortunately, you have no choice. You have to create, apply material here, apply, obviously, dummy material, and then mesh it with beam element, but then you never use it, but you have to, okay? There's no other way to, as far as I know, to create these springs. All right, so that's pretty much it. So now we're going to go to generative structure analysis. Immediately, we mesh this line with beam elements. So the beam elements right there, see that? Right there, beam mesher. You click on it. And although I say that this is the size of the element, etc., I say minimal mesh. A minimal mesh means that just don't pay attention to this number. Just give me one element from this end to the other end. That's it. That's what minimal mesh means here. And then we have to apply the cross-sectional properties. So you create the support. The actual size of this is irrelevant because these things are never used, but you have to do it. I can't remember what I did here. I put down some dummy numbers here, 0.03 feet, doesn't matter. Okay, that's good. These things will never be used. Okay, now we create a connection. Let me hide this, hide these points, because I don't want inadvertently to put clamps and restraints on these, basically unload on these points. I want to put it on the vertices at the end of the rod. So here's the connection, analysis connection, here analysis connection. First component between this, second component between that. So we create a connection between these two endpoints, and this is how we can actually define the stiffness, the spring. Okay, so if you go to the, let me move these things a little bit down. Right, I'm trying to see, just a second. I'm looking for the connection properties, which I did not put it on there. So let's go ahead and do that. Analysis connection properties. I think I must have closed it inadvertently. Let's go get it. So we go to view, toolbars, analysis connections, connection properties right there. Yeah, right there. I inadvertently closed that. Now, what we want is actually distant connection property, and the very last one, it says user defined distant connection property. You click on it, the support, you have to select this connection. That's really why I created that connection. There's nothing else you can pick here except for a connection. And it's spring rigid. You click on the wrench and you put the stiffness of the lateral stiffness or axial stiffness of the spring, 100 pound per foot. These things, these are rotational one, we're not using it. Just stiffness along the y direction is 100, right there, as you can see, right there, 100 pound per foot. Okay, so let's go ahead here. We say fine. Yep. Good. Now we're going to clamp that end. So here's a clamp that end. We are doing a static right now. We come back and do a dynamic problem later on. And then user define restraint at this point, vertex, is going to be displacement along the y is free, but everything else is fixed. Now I'm going to put a 1 pound force here. It better give me a 1 pound force, and the stiffness is 10. So 1 over 10. It better give me a displacement of 0.1 feet. Okay, this is the confirmation that it's actually right before we do the rest of the problem. So let's put a force there. This is a distributed force at that point in the direction y. I put 1 point, and when I run it, I better get 0.1 feet displacement. Okay, so it's finished. Let's plot some stuff here. I'm gonna close this, and the stuff that I don't want, I'm gonna close. Where is the deformation? Right, here's the deformation. Okay, displacement. Right there, 0.01. Oh, I'm sorry, not 0.1, because we put 1 pound, the stiffness was 100, so that's going to be 0.01 foot. Good. This is a good confirmation that it works. Now we're going to insert frequency. Insert frequency case. We use as restraint the same thing that we used just a minute ago on the static case. And remember that we have only one natural frequency here. This is a single degree of freedom system. So if you double click on this line, it says the default is extracting 10 frequencies, but we don't have 10 frequencies. If you left it like that, 10 or anything bigger than 1, it's going to come back with an error message saying that I can't do it because there's only one frequency to be extracted here. That's pretty much it. You run it and you're going to get your frequencies. And there's only one frequency, obviously, here. Finished. You go down here under the list, double click on it. It says, oh, I forgot to put the mass in there, right there. There's a mass here, right? I forgot to do that. That's why this number is wrong. So let's go ahead and do the mass now. Here's the default, here's the distributed mass on that 1 point. And the value is 1.553 slugs. Okay, this is the one that I inputted earlier when I was going through this calculation before I started the video. Okay, so that's what I put in, 1.553. And now we're going to run it, and I better get natural frequency, which is the same as what we have in the slide. What do we have in the slide? In hertz, 1.277. Let's check it out. Yep, 1.277. Good. All right, now we're going to do insert transient dynamics case, response case. You click on it. It says, okay, where is that frequency? Where are the frequencies that you extracted? Right here, there's only one frequency that I extracted. It's right there. And you say, okay. And then that's pretty much it. I need a time modulation. Okay. Remember, I need to somehow tell Catia that this is the curve that I want, or this is the curve that I want. So here's what I did. By the way, yeah. So let's go ahead and create the modulation. There's the modulation toolbar right there. You can see that. And I want a time modulation and Excel spreadsheet, browse. I do have one. That's this one. TN period followed by 0.01 TN. Say okay. All right. Actually, you can also see this. If you go to the modulation branch that was created just a minute ago, right click 2D property, I better get this graph, and this graph is supposed to be this, or the zoomed in view is supposed to be something like that. Okay, close that. All right, let's double click on this line. It says how many till what period till what time you want to simulate. Let's make it 5 seconds. And I put a 2 here, 20 here. I'll show you that you get numbers, but the numbers are not going to be matching what you're supposed to get. Okay, so say okay, and damping. The default is 1%, so this is correct. 1% is 0.01, right there. 0.01. Okay. Good. Let me move this thing out of the way. Close that. And for load, double click on it. The load is the same thing that we applied to the static case right there, another 1 pound here. And the modulation, we're going to get the select the modulation box here, and then from the tree you select modulation, time modulation. Good. I think that's pretty much it. So let's go ahead and oh, we don't even have to run it because transient dynamics, all it needs is natural frequencies, damping, and modulation. That's it. I don't have to run it. You can run it, but nothing is going to happen. So you put the cursor there, right click, you say generate 2D display. Next, finish. It says, okay, go pick the point that you want to find the displacement of. I mean, obviously, one of the points is the wall. This is the wall, and this is the mass, where the mass is sitting. Now, I want to pick this point, but it won't let me do that because there's a whole whack of things that are on the screen that are blocking me. So put the cursor there, right-click, hide. Put the cursor there, right-click, hide. And now I can go and select that point. Use node number one, right there. And then we say, okay. And if you go to this, you double click on it, you will get your choppy choppy response. A couple of things that I'm going to do before I fix this thing. First of all, the unit here, right click, format, not the unit, right click, format. I want the real to go between positive and negative instead of amplitude. The second thing is right here, right click, let me see for a second, right click options. I put the cursor on this white area, right click option, and I want the define units, which is going to be in feet, right there. Otherwise, you do, okay, yes. Now, this is fine, but I'm going to close that. We will go back to that transient dynamics instead of, I mean, even if you look at the values, they don't look right. So let me cancel this for a second. Let's go back here. Look at this again. The magnitude is, look, it goes up to a height of 0.1 foot, essentially. So what we're saying is that uh, 0.1 is down here. You can see that. I mean, it looks like the amplitude is going to be at 0.1. And the reason is that the number of sections is not correct. So let's go ahead and let's go back to Catia. Close that. Another one. And check the, yeah. You can see that when you change the number of steps, this height changes. The maximum peak height changes. So right now it's around 0.7, which is compliant with what roughly I have here. So you got to be careful. That's what this thing was about. In other words, if you do not use sufficient number of steps, basically there's a chance that you miss that. I don't know. Well, you don't miss it, but the results depend heavily on that number of steps. So let's try it again. And this is 0.8, right? Point, what is that? Roughly 0.7. And if I go here and change this to maybe, let's make this thing 9, 4 times bigger, and check the numbers. You can see it didn't change that much, okay? Almost the same as before. Now, just to confirm that I'm not playing any tricks on you, double click on this, make this thing 900, run it, or no, don't run it, but look at the results. You see, it went back to some other number. Yeah, so be careful with what you put in here. Okay, usually the way I handle it is I give it the value, look at the result, increase the value, and beyond a certain point, things don't change that much. So that is what you can trust. All right, folks. So I did not do the case where this goes instead of one period, twice the period, and then I showed you some plots here. Like here, this is when you go increase it over double the period, etc. But I did not do that. Just to confirm something here, let's go back there. I'm going to, first of all, let's put this thing back to 2000, or well, 20,000 actually. Okay, let's change the damping to 7%, 70%. So make it 70, that's xi of 0.7. So, okay. And now look at the results. There we are. Heavily, heavily damped. Okay. All right, that's pretty much it. Good luck.